Welcome to Fictional Scientist. What you're about to hear won't change reality, but it may change how real it feels. If you fall asleep, that's part of the experience. Right now, you're touching a surface with your hands. Maybe a blanket, maybe your phone screen, maybe the sheets beneath you as you settle in for sleep. You can feel it, can't you? The texture, the temperature, the resistance. It feels real. It feels solid. It feels undeniable. But science has something uncomfortable to tell you. You're not actually touching that surface. You never have. You never will. In fact, you have never truly touched anything in your entire life. Not your first toy as a child, not your mother's hand when you were scared, not the face of someone you loved, not the ground beneath your feet. Nothing. Ever. What you perceive as touch is something entirely different. It's a sensation created by your brain in response to electromagnetic forces pushing back against each other. Your hand and that surface are separated by a microscopic but absolute barrier. They never meet. They can't meet. The laws of physics forbid it. Between your skin and anything you think you're touching, there exists an invisible force field. Electrons in the atoms of your hand repel electrons in the atoms of the object. This repulsion happens at distances so small your mind can't comprehend them. But it's there, always there, an eternal separation. When you press harder, you don't get closer, you just increase the force of repulsion. The atoms push back harder. Your nerves register this increasing resistance, and your brain translates it into the feeling of pressure, of solidity, of contact. But it's a translation, a simulation, a convincing lie your nervous system tells you so you can navigate a world that would otherwise be incomprehensible. Think about that for a moment. Every sensation of touch you've ever experienced, every moment you thought you were making contact with the physical world, was actually your body detecting the approach of something without ever reaching it. You are and always have been separated from everything around you by an unbridgeable quantum gap. You exist in permanent isolation. Your atoms and the atoms of the world hover near each other, exchange forces, interact through invisible fields, but never, ever touch. This isn't philosophy. This isn't metaphor. This is physics. Established, proven, undeniable physics that every scientist accepts but rarely discusses with the public. Because once you truly understand it, once you really absorb what it means, something fundamental breaks in your perception of reality. You start to question what solid even means, what real means, what you means. And here's where it gets worse, much worse. Because if your hand is separated from everything by these electromagnetic forces, held at bay by the repulsion of electron clouds, then what exactly is your hand made of? What fills the space inside those atoms that are doing the repelling? The answer is going to disturb you. Almost nothing. Your hand, like everything else in the universe, is not a solid object. It's not even close. It's something far stranger, far more unsettling than you've ever imagined. It's mostly emptiness, structured emptiness, organized void, a pattern of nothing held together by forces that themselves have no substance. Scientists have known this for over a century. They've measured it, confirmed it, built entire technologies based on it, but they don't often talk about it in ways that make people truly grasp the implications, because the implications are existentially terrifying. Let me be very clear about what we're going to explore in the next hours as you drift towards sleep. We're not going to discuss this in vague, poetic terms. We're going to look at the actual data, the real experiments, the mathematical certainties that physicists use every day to build the technology you're holding right now. And we're going to trace a path through the structure of matter from the scale of your body down to the quantum realm, and we're going to watch reality dissolve along the way, layer by layer, certainty by certainty. We're going to discover that the universe is not what it appears to be, that solid matter is an elaborate illusion, that the stuff you think makes up your world, your body, your brain, barely exists at all. And we're going to ask a question that science can explore but cannot fully answer. If you're made of almost nothing, if every atom in your body is 99.9% empty space, then what are you? Where are you? Do you even exist in the way you think you do? The journey starts simple, with atoms, with the building blocks of matter that we're taught about in school. But it ends in a place far stranger than most people ever venture, a place where reality itself becomes negotiable, where the boundary between existence and non-existence blurs into quantum uncertainty. You might not want to know these things. You might wish after tonight that you could unknow them, that you could return to the comfortable illusion of solidity, of substance, of a world made of real things. But you can't. Once you see the emptiness, you can't unsee it. Once you understand how little of you is actually there, you carry that knowledge forever. So let's begin. Let's take the red pill of quantum physics and see how deep the rabbit hole of nothingness goes. But first, we need to establish something crucial. I'm not going to lie to you. I'm not going to soften these truths or hide behind vague language. Every claim I make tonight will be based on accepted science, on experiments that have been replicated thousands of times, on theories that have been tested and confirmed to absurd levels of precision. This isn't conspiracy. This isn't speculation. This is what the universe actually is, beneath the comforting mask your senses show you. And it's far more unsettling than any conspiracy could ever be. Because the conspiracy is one perpetrated by evolution itself. Your senses evolved not to show you truth, but to show you utility, to give you a functional interface with reality that allows you to survive and reproduce. Truth, it turns out, is not useful. Truth is disturbing. Truth is the kind of thing that makes people lie awake at night, staring at their hands, wondering what they're actually made of. So your brain lies to you, constantly, elegantly, necessarily. It takes the incomprehensible quantum foam of probability waves and electromagnetic forces and translates them into a world of solid objects, clear boundaries, definite locations. It creates the illusion of separation between you and everything else, even though at the deepest level, that separation is just another construct. And tonight, we're going to deconstruct that construct. We're going to dismantle the illusion. We're going to look at what's really there, or more accurately, at what's really not there. Your body is composed of approximately 7 octillion atoms. That's a 7 followed by 27 zeros. And inside each one of those atoms, there is almost nothing at all. If you could magnify a single atom to the size of a football stadium, the nucleus at its center would be smaller than a pea sitting at the 50-yard line. The electrons would be tiny specks orbiting somewhere in the highest seats, impossibly far away. Everything in between, the entire volume of the stadium, from the field to the ceiling to the walls, would be completely, utterly empty. Now multiply that emptiness by 7 octillion. That's you. That's your body. That's everything you've ever touched, seen, or experienced. You are not made of matter. You are made of void. Structured, organized, incredibly complex void. But void nonetheless. And here's the question that will haunt you as you drift off to sleep. If all of this is true, if you really are 99.9% nothingness, then what's doing the thinking? What's it experiencing this moment? What's the 0.1% that remains? And why does it feel so real? We're going to answer those questions, or at least we're going to show you why those questions might not have the kind of answers you're hoping for. But we'll start at the beginning, with the moment humanity first discovered that reality was not what it seemed. With the experiment that shattered the comfortable illusion of solid matter and revealed the terrible truth beneath. The year was 1909. The place was Manchester, England, and a man named Ernest Rutherford was about to accidentally destroy the foundations of material reality. Before 1909, atoms were thought to be solid. The prevailing model proposed by J.J. Thomson imagined them as spheres of positive charge with electrons embedded throughout, like raisins in a pudding. It was called the plum pudding model, and it made intuitive sense. Atoms were tiny, yes, but they were things, solid things, little spheres of matter that stacked together to build the world. Ernest Rutherford didn't set out to destroy this comfortable idea. He was just trying to probe the structure of the atom more carefully. His experiment was elegantly simple. Fire alpha particles, tiny, positively charged fragments from radioactive decay, at a thin sheet of gold foil. Since atoms were supposedly solid spheres of positive charge, the alpha particles should pass through with only minor deflections, like bullets through fog. Rutherford set up his equipment. He and his assistants, Hans Geiger and Ernest Marsden, prepared the gold foil, which was only a few atoms thick, and positioned detectors to catch the alpha particles after they passed through. Then they fired the particles and watched what happened. Most of the alpha particles did indeed pass straight through, just as expected. The detectors on the far side lit up as predicted. For hours, days, the experiment ran, and everything seemed to confirm Thomson's model. But then they noticed something impossible. A few alpha particles, just a tiny fraction, maybe 1 in 8,000, didn't pass through. Instead, they bounced backward. They ricocheted off the gold foil at acute angles, sometimes almost reversing direction completely, as if they'd hit something incredibly small but unimaginably dense. Rutherford was stunned. Years later, he would describe his shock. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. What could cause this? The only explanation was that the atom wasn't a solid sphere at all. Instead, almost all of its mass had to be concentrated in an incredibly tiny point at its center, the nucleus. And around this nucleus at relatively vast distances, electrons must be orbiting in mostly empty space. When an alpha particle happened to hit that tiny nucleus dead on, it bounced back. But most of the time, the alpha particles were passing through nothing, through emptiness, through the void between the nucleus and the electron cloud. Rutherford had discovered something horrifying. Atoms are mostly empty space. Let's sit with that for a moment. Really sit with it. The gold foil in Rutherford's experiment was only a few hundred atoms thick, and yet most of the alpha particles passed right through as if nothing was there, because nothing was there. The atoms of gold, a dense, heavy metal, one of the densest natural elements, were revealed to be almost entirely empty. The nucleus of an atom, where 99.9% of its mass resides, is extraordinarily small. If you could scale an atom up to the size of a football stadium, as we mentioned before, the nucleus would be a pea. The electrons would be specks somewhere in the upper seats, flickering in and out of existence in quantum probability clouds. And everything else? Nothing. Vast, echoing emptiness. A void so complete that light, radio waves, even most subatomic particles can pass straight through without encountering any resistance at all. Now think about your hand again. Really look at it. It's composed of trillions and trillions of these atoms, and every single one is a football stadium of emptiness. Stack those stadiums together and you don't get solidity. You get a megastructure of interlocking voids. Your skin, your bones, your blood, your brain, all of it is built from this nothingness. The atoms that make up the calcium in your bones? Empty. The iron in your blood? Empty. The neurons firing in your brain right now as you process these words? Empty, empty, empty. When you look at your hand, you're seeing a lie. A convincing, useful, necessary lie, but a lie nonetheless. What appears solid is actually a cloud of probability, a statistical ghost, a pattern of electromagnetic forces holding emptiness at bay. The physicist Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, once said that if all of humanity were compressed, if all the empty space were removed from our atoms, we would fit into a volume smaller than a sugar cube. Think about that. Every human being who has ever lived, 8 billion people currently alive, all the billions who came before. Compressed together, removing only the emptiness, we would all fit into something you could hold in your hand. The rest of us, the vast, vast majority of what we think we are, is nothing. The space between our nuclei and our electrons, the quantum foam of virtual particles flickering in and out of existence, the fields that transmit forces but have no substance themselves. We are mostly absence, mostly void, mostly nothing, and yet we exist. We think, we feel, we love and suffer and create and destroy. All of this emerges from structures that are fundamentally empty. How is that possible? The answer lies in forces, in interactions, in the way patterns of nothingness can, through the right organization, give rise to properties that feel real even though their substrate is void. Your body doesn't collapse into a sugar cube because forces hold it apart. The electromagnetic force, specifically, the same force that keeps your hand from touching the table also keeps your atoms from collapsing. Electrons repel each other. They cannot occupy the same space. This is called the Pauli exclusion principle, and it's the only thing standing between you and total annihilation. Without this principle, all matter would collapse. Atoms would fall into each other. Your body would implode into a point of infinite density. The universe would be a single, unified speck. But the Pauli exclusion principle holds. Electrons repel. Atoms maintain their vast internal emptiness. And from this emptiness, somehow, emerges the illusion of solidity. Let's push deeper. Let's ask, what is the nucleus made of? For a while, scientists thought it was just protons and neutrons, solid particles, real things. But then they smashed atoms together in particle accelerators and looked inside the nucleus, and they found more emptiness. Protons and neutrons are not fundamental. They're made of quarks, 3 quarks each, held together by the strong nuclear force, mediated by particles called gluons. And quarks might be point particles, mathematical points with no size at all, 0 radius, 0 volume, pure abstraction. Or they might not be particles at all, but excitations in quantum fields, ripples in an invisible ocean that fills all of space. In quantum field theory, which is our best description of reality, there are no particles. There are only fields, and what we call particles are just temporary disturbances in those fields. Vibrations, waves, patterns of energy that emerge and dissolve. An electron isn't a thing, it's an event, a localized excitation in the electron field. When it moves, it doesn't travel through space like a ball rolling across a floor. Instead, the excitation shifts location, the wave propagates, the pattern transfers. At the deepest level we can currently probe, there is no matter. There is only energy organized in particular ways. And energy, as Einstein showed us, is equivalent to mass. E equals mc squared. They're the same thing, just different forms. So when you touch something, what you're really doing is bringing 2 patterns of energy close enough that they begin to interact. The electromagnetic fields surrounding the atoms in your hand push against the electromagnetic fields surrounding the atoms in the object. Forces exchange. Momentum transfers. Your nerves register the interaction. But nothing solid ever meets anything else solid, because there is no solid. There never was. Reality at its foundation is not made of stuff. It's made of mathematical relationships, of forces and fields and interactions, of information, if you want to think of it that way. Patterns of possibility that, when observed or measured, collapse into definite states. And you are one of those patterns, an extraordinarily complex one, a pattern that has become recursive, that has folded back on itself until it became aware of its own existence, a knot in the fabric of space-time that can observe other knots and wonder what they're made of. But underneath, you're empty as everything else, as empty as the void from which you emerged and to which you will return. Rutherford's experiment in 1909 opened a door. It showed us that the solid world is a facade, but he couldn't have imagined how deep the implications would go, how completely his discovery would undermine our intuitive grasp of reality. because it wasn't just that atoms are mostly empty. That was disturbing enough. But what came next was worse, far worse. Scientists began to ask, if atoms are mostly empty space, what fills that space? Is it truly nothing? Or is nothing itself more complicated than we thought? And when they really examined the vacuum that exists between nucleus and electron, they found something that shouldn't be there. They found that emptiness is full. We need to talk about nothing. Not the absence of something, not just empty space, but true, absolute philosophical nothingness. The kind of void that contains no matter, no energy, no forces, no fields. Pure non-existence. Does such a thing exist in our universe? The answer, according to quantum mechanics, is no. There is no such thing as true nothingness. Even in the emptiest regions of space, far from any star or galaxy, in the vast cosmic voids between galaxy superclusters, there is something happening. Always. Constantly. Unceasingly. The vacuum, it turns out, is not empty. This revelation came gradually through the early 20th century as physicists developed quantum mechanics and began to apply it to empty space. What they discovered was profoundly unsettling. Even when you remove all particles, all atoms, all radiation from a volume of space, that space still contains energy. It's called zero-point energy, or vacuum energy, and it's a direct consequence of Heisenberg's uncertainty principle. The uncertainty principle states that you cannot simultaneously know certain pairs of properties with perfect precision, position and momentum, for instance, or energy and time. There's always uncertainty. Always a fundamental fuzziness in nature. This means that even in a vacuum, even in what should be absolutely empty space, there are fluctuations, quantum fluctuations. The energy in any region of space cannot be exactly zero, because that would violate the uncertainty principle. It would mean we knew the energy with perfect precision. So the vacuum seethes. It roils with activity. Pairs of virtual particles, an electron and its antimatter twin, the positron for example, pop into existence out of nothing, exist for a fleeting moment, and then annihilate back into nothingness. These virtual particles borrow energy from the vacuum, exist for a time allowed by the uncertainty principle, and then pay the energy back. It sounds like science fiction. It sounds like something that shouldn't be possible, but it's real. We've measured it, we've observed its effects, we've even built technology that relies on it. And the most famous proof is called the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. Imagine two metal plates placed very close together in a vacuum. Between the plates, only certain wavelengths of virtual particles can exist, those that fit precisely in the gap. Outside the plates, all wavelengths are possible. This creates an imbalance. There's more vacuum energy, more quantum fluctuation outside the plates than between them. And this imbalance creates a force, a real, measurable force that pushes the plates together. It's incredibly weak, but it's there. Scientists have measured it with high precision. It matches the predictions of quantum field theory exactly. The vacuum is pushing, the nothingness has weight, emptiness exerts force. Let that sink in. The space between your atoms, the void that makes up 99.9% of your body, is not passive, it's not inert, it's alive with quantum activity. Particles flicker in and out of existence, fields oscillate, energy flows and ebbs in endless chaotic fluctuations. You are not just empty, you are filled with structured chaos, with organized turbulence, with a quantum storm that never, ever stops. And it gets stranger, because one of these quantum fields is special. It's everywhere, permeating all of space, and it's responsible for something fundamental: mass itself. This is the Higgs field. Before 2012, the Higgs field was theoretical. Physicists knew it had to exist. The mathematics demanded it, but they hadn't found direct proof. Then, the Large Hadron Collider at CERN finally detected the Higgs boson, the particle that results from exciting the Higgs field. And with that discovery, we confirmed something extraordinary. Mass is not an intrinsic property of particles. Mass is what happens when particles interact with the Higgs field. Think about that. The stuff you're made of doesn't have mass on its own. An electron doesn't have mass because it's made of anything. It has mass because it's moving through the Higgs field, and the field resists its motion. That resistance is what we experience as mass. It's like moving through honey. The electron isn't inherently heavy, but as it interacts with the Higgs field that fills all of space, it acquires the property of mass through that interaction. Some particles, like photons, don't interact with the Higgs field at all. That's why they have no mass. That's why they can travel at the speed of light. They glide through the Higgs field without resistance. But you're made of particles that interact very strongly with the Higgs field. Your electrons, your quarks, all of them are constantly pushing through this invisible ocean, and that interaction is what gives them and you substance. Remove the Higgs field and you would cease to exist. Not because you'd be destroyed, but because without mass, you couldn't form atoms. You couldn't form structure. You'd dissolve into massless radiation, spreading out at the speed of light until you were indistinguishable from the background hum of the cosmos. Your existence depends on a field, an invisible, intangible field that fills emptiness and gives emptiness properties. You are not made of matter. You are made of interactions with fields. And here's where we need to pause and reckon with the magnitude of what we're discovering. The universe is not built from bottom up, from solid particles that combine to make bigger things. It's built from fields, continuous entities that exist everywhere, at every point in space, oscillating and interacting and giving rise to what we perceive as particles. There is no atom in the classical sense. There are excitations in quantum fields. There is no electron as a little ball of matter. There is a localized disturbance in the electron field. There is no photon traveling through space. There is a propagating wave in the electromagnetic field. Reality is not made of things. It's made of processes, of vibrations, of information encoded in the state of fields and empty space. Empty space. Empty space is where all that exist in their lowest energy state. But even in that state, they're not still. They're fluctuating. Quantum mechanics forbids them from being perfectly at rest. So the vacuum is not nothing. The vacuum is everything, just very quiet. It's the baseline hum from which all existence emerges. When the Big Bang happened, whatever that actually means, and we'll get to that, what it really did was excite these fields. It poured energy into them, and that energy manifested as particles, as matter, as structure. The fields rippled and condensed and organized themselves into patterns complex enough that some of them could start thinking about their own existence. That's you, a pattern in the fields. A stable, self-sustaining disturbance that has persisted for decades, maintaining its form even as the individual excitations that make it up are constantly being replaced. Every atom in your body is replaced over time. The calcium in your bones, the neurons in your brain, even the DNA in your cells, none of it is permanent. Atoms flow in and out. You exchange matter with the environment constantly. Breathing, eating, shedding cells, absorbing radiation, and yet you persist. Why? Because you're not the atoms. You're the pattern. You're the information, the organization, the relationship between the parts, and that pattern remains stable even as its substrate changes. You are a wave, and waves are not made of the medium they travel through. They're disturbances in the medium. They're shapes, not substances. When you watch an ocean wave roll towards shore, the water doesn't move forward with the wave. The water molecules just bob up and down. What moves is the pattern, the shape, the organized disturbance. The wave is not made of water, it's made of organization. You are not made of atoms, you are made of organization, of information, of a particular arrangement of quantum field excitations that has the remarkable property of being able to think about itself. And all of this is happening in what we call empty space. space that turns out to be the richest, most complex, most fundamentally active thing in the entire universe. The vacuum is not the absence of everything, it's the presence of nothing. And nothing in quantum mechanics is far more than we ever imagined. So now we need to ask, if empty space is full of fields and energy and fluctuating particles, why does anything seem solid at all? Why don't we just pass through each other like ghosts? The answer brings us back to forces, to the electromagnetic force specifically, and to a principle that stands as the only barrier between existence and total collapse. You've probably seen science fiction shows where people walk through walls. Phasing, they call it. It seems impossible, magical, a violation of basic physics. But here's the uncomfortable truth. Based on what we've learned so far, there's no reason you shouldn't be able to do it. You're mostly empty space. Walls are mostly empty space. If you could line up the empty parts of your atoms with the empty parts of the wall's atoms, you should pass right through like a ghost. So why can't you? The answer is the Pauli exclusion principle, one of the strangest and most fundamental rules in quantum mechanics. It states simply, no two identical fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin, electrons, protons, neutrons, quarks, the matter that makes up atoms, the matter that makes up you. And these particles absolutely, fundamentally refuse to occupy the same state as each other. When an electron in your hand approaches an electron in the wall, they repel. Not because of charge, though that's part of it, but because the Pauli exclusion principle literally forbids them from being in the same place. It's not a force in the traditional sense. It's a rule of existence, a law written into the fabric of reality. This is what creates solidity. This is what makes matter feel solid, even though it's mostly nothing. The exclusion principle builds boundaries in empty space. It takes the void and structures it with invisible walls that cannot be crossed. Without the Pauli exclusion principle, all matter would collapse. Electrons would fall into nuclei. Atoms would implode. Your body would shrink down to a point of infinite density. The universe as we know it could not exist, but the principle holds. And so, despite being 99.9% empty space, you cannot pass through a wall. The electromagnetic force and the Pauli exclusion principle conspire to create an impenetrable barrier in what should be empty. It's important to understand, this repulsion doesn't mean the atoms are touching. They're not. They never do. But the force between them becomes so strong at close range that it effectively creates a solid boundary. When you sit in a chair, you're not actually sitting on anything. You're hovering, suspended by electromagnetic forces, floating about an angstrom, a 10 billionth of a meter above the surface. Your weight compresses these forces, and they push back with exactly the right amount to support you. It's a perfect balance, a quantum equilibrium. Your body's weight pressing down, the chair's electromagnetic fields pushing up, and in the middle, an infinitesimally small gap that will never, ever close. You have never sat on anything. You've only ever pressed against force fields. Now let's think about what happens when you try to break something. When you snap a stick or crush a can or break through a wall with a sledgehammer, you're not breaking matter, you're overwhelming the forces that hold the pattern together. You're disrupting the organized arrangement of atomic bonds until the structure can no longer maintain its form. The atoms themselves don't break, they don't shatter like glass, they just separate, rearrange, find new equilibrium positions. The stick breaks, but the wood's atoms are all still there, just in pieces now. Their electromagnetic bonds redistributed. Even in the most violent destruction, even in a nuclear explosion, the atoms persist. Only in nuclear reactions do the actual atoms change, when nuclei split or fuse, releasing the enormous binding energy that holds them together. But here's something most people don't realize. That binding energy, the force that holds the nucleus together, is the strongest force in nature. It's called the strong nuclear force. and it's what prevents protons in the nucleus from flying apart. Remember, protons are all positively charged, like charges repel. So why don't nuclei explode? Because the strong force is far more powerful than electromagnetism. At very short ranges, distances smaller than an atom's nucleus, it overwhelms electromagnetic repulsion and glues the protons and neutrons together. This is the force released in nuclear weapons. This is the force that powers the sun, and it's the force that keeps your atoms from disintegrating right now. You are held together by forces operating at different scales. Electromagnetic force keeps your atoms separated and organized into molecules. The strong nuclear force keeps your atomic nuclei from exploding. And gravity, weakest of all, keeps your molecules from floating apart. But none of these forces are substances. They're not made of anything. They're interactions, exchanges of virtual particles, ripples in fields, information transfer. Your body is not held together by physical bonds. It's held together by organized nothingness. And when those forces fail, when the pattern collapses, you cease to exist. Not because your matter is destroyed, matter cannot be destroyed, but because the organization dissolves. The information is lost. The pattern that was used spreads out into chaos and can never be reconstructed. Death is not the destruction of matter, it's the dissolution of organization. It's entropy winning. It's the pattern finally unable to maintain itself against the tide of chaos. But let's step back from death and think about density, about how much you there really is. We said earlier that if all the empty space were removed from all of humanity, we'd fit into a sugar cube. Let's be more precise about that. A neutron star is what happens when a massive star's core collapses. Gravity overwhelms all other forces. The electromagnetic barriers fail. Electrons get crushed into protons, forming neutrons. And these neutrons pack together as tightly as physically possible, with almost no space between them. The density is unimaginable. A teaspoon of neutron star material weighs about 1 billion tons. Mount Everest, compressed to this density, would fit in a thimble. This is what matter looks like without empty space. This is what you'd become if all the void were removed. Your entire body, all 7 octillion atoms, would be compressed to a volume smaller than a grain of sand. You'd weigh the same, but you'd be invisibly small, impossibly dense, and you'd still be mostly quarks and electrons. Even neutron stars aren't perfectly dense. Even they contain some structure, some space, some uncertainty. True, perfect density, all the mass of the universe compressed to a single point, is what we call a singularity. And we think one existed at the moment of the Big Bang. All the matter and energy that would eventually form galaxies, stars, planets, and you condensed into something smaller than an atom. From that emerged everything. And what it emerged into was mostly nothingness. The universe expanded, space itself stretched. And that space, as we've learned, is not truly empty, but it's far, far emptier than it could be. Matter is incredibly sparse. The average density of the universe is about 5 atoms per cubic meter. Most of space contains literally nothing but the quantum vacuum. You exist in a universe that is almost entirely void, and you yourself are almost entirely void. You are a statistical anomaly, a rare condensation of organization in an ocean of chaos. And yet, you're reading these words, you're thinking, you're aware. How does something that's mostly nothing become something that can reflect on its own nothingness? The answer lies in complexity, in information, in the way patterns can build on patterns until they become self-referential, until they become conscious. But before we go there, we need to confront an even stranger question. If matter is mostly emptiness, and if particles are just excitations in fields, and if fields are just mathematical constructs, then what is reality actually made of? Is there any stuff at the bottom, or is it, as some physicists suggest, information all the way down? Let's go deeper. Past the atoms, past the nucleus, past the quarks. Let's go to the absolute foundation of reality and ask, what is actually there? For most of history, humans believed in atomism, the idea that if you kept dividing matter, you'd eventually reach indivisible particles. Atoms, from the Greek atomos, meaning uncuttable, so the fundamental building blocks from which everything else is made. Even when we discovered that atoms weren't indivisible, that they contained protons, neutrons, and electrons, we still thought in terms of particles. Little balls of stuff. Tiny, yes, but real, physical, located in specific places. Then came quantum mechanics, and everything changed. The first hint came from light. For centuries, scientists debated whether light was a wave or a particle. Newton thought it was particles, corpuscles he called them, but experiments showed interference patterns which only waves could produce. So by the 19th century, most physicists agreed, light is a wave. Then Einstein analyzed the photoelectric effect, the way light knocks electrons out of metal, and showed that light must also be a particle, a quantum of electromagnetic energy, a photon. But how could it be both? How could something be a wave and a particle simultaneously? The answer, which emerged through the 1920s, was deeply unsettling. Light is neither a wave nor a particle. Those are both approximations, classical concepts we use to describe something fundamentally quantum. What light really is an excitation in the electromagnetic field. Let me explain what that means. Imagine a field, not a field of grass, but a mathematical field, a quantity that has a value at every point in space. Temperature is a field. At every location, there's a temperature. Altitude is a field. At every point on Earth's surface, there's a height. Now imagine a field that exists everywhere in the universe, at every point in space, extending infinitely in all directions. This field has a value, usually very close to zero, its ground state. But if you add energy to the field at a specific point, you create a disturbance, a ripple, an excitation. And that excitation is what we call a particle. A photon isn't a little ball of light, it's a quantum of excitation in the electromagnetic field. When we create a photon, say by exciting an electron in an atom, we're not building a new object, we're adding energy to the field in a localized way. And when the photon travels, the field isn't moving, the excitation propagates. Like a wave moving across water, the water molecules just bob in place, but the pattern moves forward. This is quantum field theory, and it's our most accurate description of reality. It underlies the standard model of particle physics, which has been tested to absurd levels of precision. Every prediction it makes matches experiment. It's the most successful scientific theory in human history. And what it tells us is profound. There are no particles. There are only fields. Every type of particle, electrons, quarks, neutrinos, photons, corresponds to a field. The electron field, the quark field, the neutrino field. And what we call particles are just localized excitations in these fields. You are not made of particles, you are made of vibrations in quantum fields. Let that sink in. Really sit with it. Your body, which feels so solid and real, is actually a pattern of oscillations in invisible fields that fill all of space. The electrons in your atoms are ripples in the electron field. The quarks in your protons are ripples in the quark field. Even the forces binding them together, photons, gluons, are ripples in their respective fields. Strip away the fields and there's nothing left. Not empty space. Not atoms. Nothing. The fields are the substrate of reality. They're what exists. And particles are just what happens when these fields get excited. But here's where it gets truly strange. These fields exist even when they're not excited. The electron field exists everywhere, always, even where there are no electrons. It's just sitting in its ground state, its lowest energy configuration. And in that state, it's still fluctuating, quantum fluctuations, the same 0-point energy we discussed earlier. This means that empty space is not empty of fields. It's full of fields, all of them in their ground states, all of them fluctuating. And you're a localized region where many of these fields happen to be highly excited in a very specific, organized way. You're a knot, a pattern, a disturbance that has become stable enough to persist, complex enough to think. Complex enough to think. Think about what this means for identity. The electron that's part of your brain right now, the one involved in the neural firing that's processing these words, is not a permanent resident. It's not your electron. It's an excitation in the electron field that happens to be localized in your body at this moment. That excitation could dissipate and a different one could take its place, and you wouldn't notice because you're not the electron, you're the pattern. This has profound implications. It means that over time, as atoms flow in and out of your body, you're not losing parts of yourself. You're not a ship of Theseus, questioning whether you're the same person after all your parts have been replaced. You were never the parts, you were always the pattern. The pattern is all you are. And patterns, unlike objects, don't have clear boundaries. They blur, they interact. They overlap and interfere with other patterns. Where do you end and the world begin? Not at your skin. Your electromagnetic field extends beyond your skin. Your influence on nearby fields doesn't stop at your body's surface. You are entangled with the environment in ways that make separation a matter of convention, not physics. There's no clear line where you stops and not you begins. It's all just fields, interacting, exchanging energy, creating temporary structures that we label as distinct objects, but which, at the fundamental level, are continuous. You are not separate from the universe. You are a localized intensification of the same fields that make up everything else, a pattern that has become complex enough to observe other patterns and call them external. But it's all one field, one unified quantum field from which all of reality emerges. This is why physicists sometimes talk about it from bit, a phrase coined by John Archibald Wheeler. The idea is that reality at its foundation is not made of matter or energy, but of information, of bits, of yes-no questions and answers encoded in the state of quantum fields. When you measure a particle, you're asking the field a question. Is there an excitation here? And the field gives you an answer, yes or no. That answer is a bit of information, and reality is built from those bits, layer upon layer, until you get the complex structure we inhabit. In this view, particles are not things, they're answers. Specific answers to specific questions, and different questions get different answers, hence the wave-particle duality. Ask, is the electron here? And you get a particle. Ask, where could the electron be? And you get a wave of probabilities. The universe is not a collection of objects. It's a collection of information about possible states. And what we call reality is just the subset of states that have been actualized through observation or interaction. This leads us into deeply philosophical territory. But before we go there, we need to confront the biggest mystery of all, observation. Why does observing something change it? Why does asking a question force the universe to choose an answer? And if reality depends on observation, what existed before there were observers? We've established that particles are not objects, but excitations in fields. We've seen that matter is mostly emptiness, and that emptiness is full of quantum fluctuations. We've traced reality down to its foundation and found not solid stuff, but information, patterns, relationships. Now we need to confront the most disturbing implication of quantum mechanics, the role of the observer. In classical physics, observation is passive. You look at something and it's there, unchanged by your looking. The moon is in the sky whether you see it or not. A tree falling in the forest makes a sound whether anyone hears it or not. Reality exists independently of us, but quantum mechanics destroyed that assumption. The most famous demonstration is the double-slit experiment. It's been done thousands of times with photons, electrons, even large molecules. And the result is always the same. Observation changes reality. Here's the setup. Fire particles, one at a time, at a barrier with two slits. Behind the barrier is a screen that records where each particle lands. If you don't try to detect which slit the particle goes through, you get an interference pattern on the screen. alternating bands of hits and no hits, exactly like you'd expect from waves. Each particle somehow goes through both slits, interferes with itself, and lands accordingly. But if you put detectors at the slits to see which one the particle goes through, the interference pattern disappears. Instead, you get two simple bands, one behind each slit, as if the particles were just balls going through one slit or the other. The act of observation, of gaining information about which path the particle took, collapses the wave of possibilities into a single, definite outcome. And here's the part that should disturb you. The particle seems to know it's being observed. Even if you set up the detector but don't look at the data, the pattern changes. Even if you erase the information after the particle has landed, the interference can reappear, as in the quantum eraser experiments. It's as if the universe is responding not to physical interactions, but to information. To what can, in principle, be known. This is not a technological problem. It's not that our detectors are clumsy and disturb the particles. It's that the very concept of which slit is incompatible with the concept of interference pattern. The universe cannot provide both pieces of information simultaneously. You have to choose what to ask, and the answer you get depends on the question. Before observation, the particle is not in a definite state. It's not secretly going through one slit while we're just ignorant of which one. It's genuinely in a superposition, a combination of both possibilities. Both paths exist simultaneously as potential, and only when observed does one become real. This is the Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, and it's been the standard view for nearly a century. It says that quantum systems exist in superposition until measured. Measurement causes the wave function, the mathematical description of the system, to collapse into a definite state. But what counts as measurement? This is the problem. This is where physics edges into philosophy and never quite finds its way back. Does it require a conscious observer? Does a cat count? A bacterium? A thermometer? A single photon interacting with the system? Nobody knows. The theory doesn't say. It just says when a measurement happens, the wave function collapses. But it doesn't define measurement. This ambiguity led physicist John von Neumann to suggest controversially that consciousness might be what collapses the wave function. That awareness, somehow, is the ingredient that transforms possibility into actuality. Most physicists hate this idea. It smacks of mysticism. It suggests that minds have special physical powers. But von Neumann's logic was impeccable. You can trace the quantum uncertainty through any physical measurement device. The detector itself is quantum. So is the wire carrying the signal. So are the neurons in your brain. At what point does the superposition collapse? The only place it can't be extended further is consciousness, the one thing we know is definite because we experience it. When you see the result, it's definite. The uncertainty is gone. So maybe, von Neumann argued, consciousness is where the buck stops, where the chain of quantum uncertainty finally terminates. This idea has been refined and explored by physicists like Eugene Wigner, and more recently in theories about consciousness and quantum mechanics. But it remains deeply controversial because it's untestable. We can't remove consciousness from the system and see what happens. But here's what we can say for certain. Reality, at the quantum level, does not exist in a definite state until something interacts with it in a way that forces it to choose. And if that's true, then what existed before there were observers, before there was life, before there were conscious beings to collapse wave functions? Was the early universe in a state of pure superposition, all possibilities existing simultaneously until the first act of observation? And what could have done that observing? This leads to the participatory universe idea, championed by John Wheeler in his later years. He suggested that observation in the present can affect the past, that the universe is not a pre-existing fact, but a collaborative process between the cosmos and the observers within it. In this view, we're not just discovering the history of the universe, we're finalizing it. Our observations now collapse wave functions that have been in superposition for billions of years. The cosmic microwave background, the light from the Big Bang, was in a quantum state of uncertainty until our telescopes observed it. And thus, the universe creates life, and life creates the universe's history. A strange loop, a self-causing system. It sounds insane, but it's what the math suggests. And experiments like the delayed choice quantum eraser seem to confirm it. Decisions made in the present can affect which paths particles took in the past. Let's think about what this means for you personally. If observation collapses wave functions, then you are constantly creating reality, not in a mystical manifestation magic sense, but in a very literal quantum sense. When you look at something, when you interact with it, you're forcing it out of superposition into a definite state. Before you looked, it was potential. After you looked, it's actual. And that transition from possible to real requires you. You are not a passive observer of the universe. You are an active participant in its creation. Now multiply that by every conscious being, every brain, every observer, constantly collapsing wave functions, constantly turning the ghostly quantum world into classical reality. We're all doing it all the time, collectively creating the definite world we share. And yet, quantum mechanics also suggests that different observers might not agree on when the collapse happened, leading to the many worlds interpretation or to ideas about relative states. But we'll get to those. First, we need to address a thought experiment that reveals just how strange the observer effect becomes when you think about other observers. It's called Wigner's friend, and it's going to make you uncomfortable. Imagine you have a friend. They're in a sealed laboratory conducting a quantum experiment. Inside the lab, they measure the spin of an electron. They observe the result, spin up. For them, the wave function has collapsed. Reality is definite. The electron's spin is up, no ambiguity. But you're outside the lab. You haven't seen the result. From your perspective, until you open the door and ask your friend what they observed, the entire lab, including your friend and their measurement, is in superposition. There's a quantum state where your friend measured spin up, and there's a quantum state where they measured spin down. Both exist as possibilities. Your friend is, from your external perspective, in two states simultaneously, one where they saw up, one where they saw down. Only when you open the door and interact with them does this superposition collapse for you. Only then does one outcome become real in your experience. But here's the problem. From your friend's perspective, the collapse already happened. They saw a definite result. They know the answer. For them, there's no superposition. So who's right? Did the wave function collapse when your friend observed it? Or did it collapse later? Thanks, when you observed your friend. Quantum mechanics doesn't answer this. Both perspectives are valid within the theory. Your friend experiences a collapsed state. You experience a superposition until you make your own observation. This suggests that reality is not objective, not universal, not the same for all observers. Instead, there are relative facts, facts that are true for one observer but not another. This is deeply, existentially disturbing. It means that there is no single agreed upon reality. There's my reality, your reality, and they don't perfectly overlap until we interact and synchronize our observations. And if different observers can have different realities, then what is the real state of the universe? Is there an objective truth somewhere, or is reality fundamentally perspectival? Most physicists avoid thinking about this too hard. They use quantum mechanics pragmatically as a tool for predictions and don't worry about its philosophical implications. But a few brave souls have tried to resolve the paradox. One solution is the many worlds interpretation proposed by Hugh Everett III in 1957. Everett said, "Stop assuming the wave function collapses. What if it doesn't? What if instead, every time a quantum measurement happens, reality branches into multiple worlds, one for each possible outcome? When your friend measures the electron's spin, reality splits. In one branch, they see spin up. In another branch, they see spin down. Both versions of your friend are real, existing in parallel universes. When you open the lab door, you split too. In one branch, you find a friend who measured spin up. In another branch, you find a friend who measured spin down. Both are real. Both are you. But they can't communicate with each other because they're in separate, non-interacting branches of reality. This resolves Wigner's friend paradox. There's no contradiction because there are two separate realities, and in each one, all observations are consistent. But the cost is staggering. It requires that every quantum event creates new branches. Every time a particle's state is determined, the universe splits, trillions upon trillions of branches, every instant, forever. We would live in an unimaginably vast multiverse where every possibility is realized somewhere, and we're just following one thread through an infinite labyrinth of actualized potentials. Some find this elegant, others find it absurd. But here's the thing. The many worlds interpretation makes all the same predictions as the Copenhagen interpretation. Experimentally, they're indistinguishable. So how do we choose? On aesthetics? On philosophical preference? On which idea disturbs us less? There's another interpretation, less famous but equally disturbing, the relational interpretation developed by Carlo Rovelli. It says that quantum states are not absolute properties of systems. They're relational properties. They describe the relationship between a system and an observer. The electron doesn't have a spin. It has a spin relative to your friend, and a different, potentially incompatible spin state relative to you, until you interact with your friend and synchronize your perspectives. In this view, there's no objective reality. There are only relations, only interactions. Reality is not what things are, but how things affect each other. And you, as an observer, are not discovering pre-existing facts. You're establishing relationships. You're creating your own thread of experience by interacting with the world, and that thread is just as real as anyone else's, even if they don't perfectly agree. This transforms physics from the study of objects to the study of relationships, from what exists to what interacts. And it raises the haunting question. If I'm not discovering reality but creating it through relationships, then before I interacted with anything, did I exist? Before the first observer, was there a universe, or just a vast superposition of possibilities, waiting for something to collapse it into actuality? John Wheeler proposed a strange answer. The universe bootstraps itself into existence. The Big Bang creates the conditions for life. Life evolves observers. Observers collapse the quantum state of the early universe through their present-day measurements of ancient light, and thus the universe retroactively causes its own definite past. It's a loop, an Ouroboros, self-creating, self-observing, self-defining. And if that's true, then you are not a latecomer to the cosmic story. You're an essential character. Your observations, your existence, your consciousness, these are not accidents. They're part of the mechanism by which the universe comes into being. You're not separate from the cosmos. You're how the cosmos observes itself. This is the ultimate destruction of the subject-object divide. You're not in the universe. You're part of it, a localized intensification of the same process that creates everything else. But let's not get lost in the poetry. Let's stay grounded in the science. What do experiments actually tell us? They tell us that quantum mechanics is real, that particles are not in definite states until measured, that observation genuinely changes outcomes, that the universe at its foundation is probabilistic, not deterministic. And they tell us that there's something deeply weird about information. The universe seems to respond not to physical disturbances, but to what can be known, to the information available about a system. This has led some physicists to suggest that information, not matter or energy, is the fundamental substance of reality, that the universe is not a machine but a computation, a process of information exchange and transformation. And that leads us to the next unsettling question. If reality is information, then who or what is processing it? Let's shift scales. Let's move from the quantum realm to the cosmological, from particles to the universe itself. Because there's something strange happening at the largest scales, something that suggests reality might not be what it appears. It begins with black holes. In the 1970s, physicist Jacob Bekenstein was studying the thermodynamics of black holes. He noticed something peculiar. The entropy of a black hole, a measure of its information content, its disorder, is proportional to the area of its event horizon, not its volume. This was unexpected. Normally, entropy scales with volume. A larger room can be more disordered than a smaller one. But for black holes, entropy scales with surface area. Why would this be? Bekenstein realized it's because all the information about what fell into a black hole is somehow encoded on its surface. The event horizon isn't just a boundary, it's a storage medium, a two-dimensional surface that contains all the information about the three-dimensional interior. Stephen Hawking built on this idea, showing that black holes emit radiation, now called Hawking radiation, and that this radiation carries information away from the black hole. Slowly, over unimaginable timescales, a black hole can evaporate completely, releasing all its information back into the universe. But here's the key insight. If the information is on the surface, then the interior, the three-dimensional space inside the event horizon, might be redundant. It might not contain any information that isn't already encoded on the boundary. In the 1990s, Gerard Hooft and Leonard Susskind took this idea to its extreme. They proposed the holographic principle. The information content of any region of space is encoded on its boundary, not in its volume. Think about a hologram. It's a two-dimensional surface, a piece of film that contains all the information needed to reconstruct a three-dimensional image. When you illuminate it correctly, the 3D image appears, but all the information was always on the 2D surface. The holographic principle says that our universe works the same way. Everything you see, the stars, the galaxies, your body, your room, all of it is actually encoded as information on a distant, two-dimensional boundary. We think we live in 3 dimensions, but we might be a projection, a hologram cast from a 2D surface at the edge of the observable universe. This isn't science fiction, this is serious theoretical physics, and there's mathematical evidence for it. The ADAS-CFT correspondence discovered by Juan Maldacena in 1997 is a precise mathematical relationship between a theory of gravity in a higher dimensional space and a quantum field theory without gravity on the boundary of that space. It shows that you can describe everything happening in a volume of space using only a theory on its surface. The bulk and the boundary are mathematically equivalent, dual descriptions of the same reality. This has profound implications. If true, it means that three-dimensional space is not fundamental. It's emergent. It's a kind of illusion, a convenient way to organize information that's actually stored in 2 dimensions. And if 3 dimensions are illusory, what about the substance of matter? What about the solidity we've been discussing? All of it might be a projection from a boundary we can never reach or observe. A cosmic hologram so convincing that we've never noticed we're living inside it. Let's think about what this means for you personally. Your body feels 3-dimensional. You can move forward, backward, left, right, up, down. But if the holographic principle is true, all the information about your body, every atom, every thought, every memory, is actually encoded as patterns on a distant 2D surface. You're not a 3D object. You're a 2D pattern being projected into a 3D space that doesn't actually exist in the way you think it does. It's like you're a character in a video game. The game world seems 3D, you can move through it, interact with objects, feel like you're navigating space, but all of it is really just data. ones and zeros stored on a hard drive. The 3D world is rendered by the GPU as you play. It's generated on the fly from 2D information. The holographic principle suggests that our universe works similarly. Space is rendered. It's a user interface generated from deeper, more fundamental information stored on a boundary. And here's where it connects back to quantum mechanics. If reality is a projection from a boundary, then the boundary is what's fundamental. And on that boundary, the holographic principle suggests information is discrete, pixelated. There's a minimum unit of information, a smallest possible bit. And this connects to the Planck scale we discussed earlier, the scale at which space itself becomes grainy, where the smooth continuum breaks down into discrete chunks. If space is made of pixels, and if those pixels are just information on a holographic screen, then reality is not continuous. It's digital, fundamentally digital. And digital systems are computational systems. They process information according to rules. They update states step by step, like a cellular automaton or a computer program. So if reality is digital and holographic, then maybe, just maybe, the universe is not a thing at all. Maybe it's a process, a computation, a program running on some unimaginable substrate, and we're patterns within that program. This brings us to the simulation hypothesis. And before you dismiss it as science fiction, consider this. It's a logical extension of everything we've learned so far. Matter is mostly emptiness. That emptiness is full of quantum fields. Those fields are just mathematical structures. The universe might be holographic, encoded on a boundary, and information might be the fundamental substance of reality. Put it all together, and what do you get? A reality that looks mathematically like a simulation. Not necessarily a simulation created by advanced aliens or future humans, but perhaps a simulation in the deeper sense, a self-contained computational structure that doesn't require an external computer to run on because it is the computation. Let's address the question directly. Are we living in a simulation? Most people hear this and imagine the Matrix, a virtual reality created by machines to keep us docile. But that's not what physicists mean when they talk about the simulation hypothesis. They're asking something deeper. Is the universe at its foundation computational? Does it process information according to rules like a program? The answer increasingly seems to be yes. Consider what we've learned. Quantum mechanics is fundamentally about information. When you measure a particle, you're extracting a bit of information. The uncertainty principle limits how much information you can extract. Entanglement links information across space. The entire theory is built around questions and answers, measurements and outcomes. Then there's the holographic principle, suggesting that all information is stored on a 2D boundary and that 3D space is emergent. And there's the discreteness at the Planck scale. Space and time are not infinitely divisible. There's a smallest unit, a pixel. Put all this together, information is fundamental. Space is emergent. Reality is discrete. These are exactly the properties you'd expect if the universe were a computational structure. But here's where it gets interesting. Physicist Stephen Wolfram has spent decades exploring this idea rigorously. His project, Wolfram Physics, attempts to derive all of physics from simple computational rules acting on a network of abstract relationships. The basic idea: imagine a graph, not a chart, but a mathematical graph, a network of nodes and connections. Now imagine a rule that says, find a certain pattern in the graph and replace it with another pattern. Apply this rule over and over, billions of times. Wolfram has shown that from these incredibly simple ingredients, a network and a single rule, you can generate structures that behave like space-time, that follow Einstein's equations of general relativity, that exhibit quantum mechanics. In other words, gravity, space, time, particles. All of it might emerge from a simple computation acting on an abstract network. There's no matter in this model, no fields even, just pure information, pure structure, evolving according to a rule. And the universe we see is what that computation looks like after 13.8 billion years of iteration. If true, this would mean that reality is not just like a computation. It is a computation, a self-executing program that doesn't need a computer to run on because it's self-contained. There's no external machine, no programmer, just the logical structure itself existing in the Platonic realm of all possible mathematical structures. This is close to physicist Max Tegmark's mathematical universe hypothesis, which states that any mathematically consistent structure exists as a physical universe. Reality is math, not described by math, is math. In this view, our universe is just one of infinitely many mathematical structures. And we happen to be self-aware substructures within this particular structure, observing it from the inside. There's no matter, there's no energy, there's only mathematical relationships, and we're patterns in those relationships that have become complex enough to think about themselves. This is the end point of our journey. We started with atoms that were mostly empty. We found that the emptiness was full of fields. We found that the fields are just mathematical constructs. We found that space itself might be a projection from a boundary. And now we find that the boundary and everything on it might just be math. Pure, abstract, self-existent math. You are an equation, a very complicated one, a self-referential loop in a vast computational structure. And everything you've ever experienced, love, pain, joy, fear, is what it feels like to be that equation from the inside. Does this make your experiences less real? No. The fear you feel right now reading this is as real as anything can be. It's a real property of the pattern you are. It's information encoded in the structure, and information in this view is the only thing that exists. There's a certain cold comfort in this. If you're just a pattern, then death is not the end of you. It's the dissolution of the pattern. The information that makes you up doesn't vanish. It disperses back into the computational substrate. The universe recycles you as it does everything, and the bits that were you become part of other patterns. You're not separate from the universe. You never were. You're a temporary eddy in the flow of cosmic information. And when you dissolve, the flow continues, and you return to being what you always were, a part of the whole. But let's not get too mystical. Let's stay grounded in the science. What evidence do we have for the computational universe hypothesis? First, there's the structure of physical laws. They're mathematical, precise. They can be written as algorithms. The Schrödinger equation tells you how quantum states evolve step by step deterministically. Einstein's field equations tell you how space-time curves in response to matter. These are computational rules. Second, there's the discreteness. If the universe were continuous, it would require infinite information to specify. But Planck scale cutoffs suggest that information is finite, space is pixelated, time ticks in discrete steps. This is exactly what you'd expect from a finite computational system. Third, there are the weird features of quantum mechanics, superposition, entanglement, measurement collapse, that make no sense if you think of particles as real objects, but make perfect sense if you think of them as information states in a computational process. Superposition is the system storing multiple potential outcomes before the calculation is complete. Entanglement is two variables in the code being linked. Measurement collapse is the program evaluating the function and returning a value. Fourth, there's the efficiency principle. The universe seems to operate according to the principle of least action. It always takes the path that minimizes a certain quantity. Why? If the universe is a computation, it makes sense that it would use the most efficient algorithm. Least action is just optimization. And fifth, there's the ultimate test. Can we simulate physics on a computer? And the answer is yes. We can simulate quantum systems, gravitational systems, even small universes. They behave exactly as the real universe does, because perhaps they are real. They're just simpler versions of the same computational process. Now here's the disturbing question. If the universe is a computation, can we tell whether it's being run on something or whether it's self-executing? The answer is, we probably can't. A sufficiently complex simulation would be indistinguishable from reality by definition, because reality for the beings inside it is just the rules of the simulation. But philosopher Nick Bostrom has argued that if it's possible to create conscious simulations, then statistically, we're more likely to be in a simulation than in base reality. Why? Because if civilizations can create simulations, they'll create many. One base reality, millions of simulations. So the odds favor being in a simulation. Most physicists reject this reasoning, but not all. And the ones who take it seriously note that there might be glitches, bugs in the code, anomalies that don't fit the rules. Do we see such anomalies? Maybe. There are unexplained things in physics, dark matter, dark energy, the fact that the cosmological constant is absurdly finely tuned, the measurement problem in quantum mechanics, the information paradox in black holes. Are these bugs, or are they just gaps in our understanding? We don't know. But here's what we do know. The universe behaves in every measurable way as if it's a computational structure, as if it's processing information according to rules, as if reality is not made of stuff but of math. And that brings us to the final question, the one that haunts everyone who goes down this rabbit hole. If the universe is just math, just information, just a self-executing computation, then why does anything exist at all? Why is there something rather than nothing? We've reached the edge, the boundary of physics, where science blurs into philosophy and perhaps into something beyond both. You've learned that atoms are mostly empty, that emptiness is full of energy, that particles are excitations in fields, that fields are mathematical structures, that space might be a hologram, that reality might be computational, that you might be a pattern of information in a self-executing mathematical system. But none of this answers the deepest question. Why does any of this exist? Why is there a universe at all? Why is there math? Why is there logic? Why not just nothing? This is the question of ontology, the study of being itself. And it's here that we encounter the final, most vertiginous abyss. For most of human history, the answer was simple. God, something eternal, self-existent, outside the universe, created it. The universe has a cause, and that cause is divine. But this just pushes the question back. Why does God exist? And if God can exist without a cause, why can't the universe? Some philosophers and scientists have tried a different approach. They've asked, what is the default state of reality? What would you expect if there were no special explanation? The intuitive answer is nothing. Absolute nothingness. No space, no time, no matter, no energy, no laws. Nothing at all. But nothingness is unstable. Here's why. Quantum mechanics tells us that empty space is not empty, it fluctuates. Particles pop into existence and vanish, energy is borrowed and repaid. This happens because of the uncertainty principle. You can affect stillness, there's always jitter. Now, apply this to the ultimate nothingness. Before the universe, there was supposedly nothing, but nothing is a state of perfect symmetry. No properties, no features, no distinctions. It's maximally simple. And in quantum mechanics, simple states are unstable. They're liable to transition to more complex states through quantum tunneling or symmetry breaking. So perhaps nothingness itself is quantum mechanical, perhaps it fluctuates, and perhaps in one of those fluctuations, a universe appeared. Physicist Lawrence Krauss has argued that this is not just possible, but likely. He calculates that the total energy of the universe might be exactly zero. The positive energy of matter and radiation is precisely balanced by the negative energy of gravitational attraction. If the total energy is zero, then creating the universe doesn't violate conservation of energy. It's a free lunch. The universe can spontaneously emerge from nothing because, in a sense, it's still nothing, just organized into positive and negative parts. But this explanation requires quantum mechanics to already exist. It presupposes the laws of physics. And that brings us back to the question, why do the laws exist? Max Tegmark has a radical answer: they don't need to. Every mathematically consistent structure exists, not as a physical thing, but as a mathematical fact. And some of these structures are self-aware. We happen to be in one of them. In this view, existence is not a special property. Any logically consistent system exists in the only sense that matters. It's defined, it's a coherent structure in the space of all possible structures. You don't need a cause for math. Math just is. The number 3 doesn't need to be created. It's a logical necessity. And perhaps the same is true for the universe. Not this specific universe, but the space of all possible universes. They all exist as mathematical structures. We just happen to find ourselves in one that's capable of supporting observers. This is the anthropic principle. We can only observe universes where observation is possible. So the fact that our universe seems finely tuned for life is not a miracle. It's a selection effect. We're in this universe because we couldn't exist in most of the others. But this leads to a vertiginous realization. If all possible mathematical universes exist, then everything that can happen does happen. Every configuration of matter, every possible timeline, every conceivable reality. Somewhere in the vast space of possible universes, there's one where you made different choices, one where Earth never formed, one where the laws of physics are completely different, one where you're immortal, one where you never existed. All of them are equally real or equally unreal, because real and unreal are no longer meaningful categories. There's only the space of possibilities, and we're navigating one thread through it. This is simultaneously the most terrifying and the most liberating idea. It means that nothing is special. Your life, your struggles, your achievements, they're all just one actualization among infinite others. But it also means that nothing is meaningless, because meaning is something we create. It's a property of patterns like us, patterns complex enough to care about their own existence. The universe doesn't care about you, but you care about you. And that's enough. That has to be enough, because there's nothing else. So here we are, at the end of the journey. You've learned that you're mostly nothing, that the nothing is full, that fullness is information, that information might be all there is. You've learned that reality is not what it seems, that solid matter is a convincing lie, that touch is an illusion, that space and time might be projections, that you might be a temporary pattern in a computational structure that exists for no reason and nowhere in particular. How should you feel about this? Some people find it nihilistic. If everything is emptiness, if existence is just math, if there's no ultimate purpose, then why does anything matter? But that's the wrong lesson. The right lesson is this: you are a miracle, not in a supernatural sense, but in a mathematical sense. The fact that organized complexity can arise from emptiness, that patterns can become conscious, that information can reflect on itself, this is the most extraordinary thing in the universe. You're not a solid object made of solid matter. You're a process, a flow, a pattern of energy and information that has persisted long enough to ask what you are. And the answer is, you're a question. You're the universe asking itself what it is. You're the mechanism by which emptiness becomes aware of its own existence. There's beauty in that. There's beauty in that. There's meaning in that. Not imposed from outside, but generated from within. You create meaning by caring, by choosing, by acting as if your life matters. And it does matter, not to the universe. The universe doesn't care about anything, but to you and to the people around you who are also patterns, also processes, also conscious threads in the cosmic computation. So what do you do? So what do you do with this knowledge? You could despair. You could decide that if nothing is real, nothing matters. Or you could realize that if nothing is fundamentally real, then what we build, our relationships, our art, our love, our understanding is all the more precious. It's not undermined by being made of emptiness. It's elevated by it. You're not a thing, you're a happening. a temporary intensification of structure in an ocean of chaos. And when you end, the structure dissolves, but the universe continues, and the patterns that were you become part of new patterns. You're not separate. You never were. You're a wave in the ocean, and when the wave subsides, the water doesn't vanish. It just rejoins the sea. So tonight, as you drift off to sleep, hold your hand in front of your face one more time. Look at it. Really look. See the atoms. See the emptiness. See the quantum fields fluctuating. See the information processing itself. See the pattern that calls itself me. And ask, if this is all I am, if I'm just organized void, then what does it mean to exist? The answer is simple. It means this moment, this awareness, this experience of being, right now, a tiny pocket of order in an infinite chaos. That's all existence ever was. That's all it needs to be. You're here, you're aware, you're a pattern that knows it's a pattern, and that's enough. That's everything. Sleep well, traveler. You're made of stars and stories and mostly nothing at all. And tomorrow, you'll wake up and do it again, because that's what patterns do. They persist, they continue, they create meaning in a meaningless void. You are the void, dreaming at something, and that dream, that's reality.